All right, hey guys, again, last video, I just went through the quiz results, reviewed that it was out of 44 points. Here are your percentages right there, and then here's how I broke down each question. And I also went through the class summary. How did the class do? And ideas for how to improve based on if you got a B, here's what you can do. If you got a C, here's what you can do. And if you got a D or an F, here's what you can do. These are my ideas at least. Of course, your other teachers, your parents, your friends might have other ideas, so ask them, but I can only give you my ideas for what I've seen work in the past year. The purpose of this video, this is the second video right now, is to show you how you can find feedback for any of the problems that you did here, okay? So I have here on the lower slides, notice this here, down here, right down here, okay? This PowerPoint's moving, I didn't want that to happen. I wanted to highlight that down here. Class summary's moving around, ignore that, ignore this for a second. It's going wrong here. See here, number one, click on it, number one. There we go, here's number one here. Boom, there you go. Simple as that. We got student IDs here. Find your student ID. It should be on the same place on every single slide. So if you're 2006645, and email me if you forget your number, right? If you're, well, what did I tell you again? It should be in Synergy, your student ID. But if you sent me a fake number or something that's like supposed to confuse other people in case they knew your student number, then just email me and I can look it up for you. Okay, so you're on row 14 if you're 2006645, and you got this one right because it says yes here. All right, so if it says yes, you have full credit. Remember, the first 20 problems, 2 points each. Last one is 4 points each. So yeah, people are good at finding collinear points. We're good to go here. These are 3 collinear points, and then other people said other 3 collinear points. And that was fine too. I only put it down here if I marked it off. If I put an X mark here, that means you got it incorrect. So you didn't get the 2 points here. So this was a person who put down 2 letters for each point. Remember, points are names with 1 letter, got to be uppercase. So that's explained to you here. So this is teacher feedback. This is directly from me. All right, number 2, let's do this. We can just go through them all real quick, perhaps. All right, so this was name 3, at least 3 coplanar points that are non-collinear. All these points are coplanar because this is a planar figure. It's drawn on a sheet of paper, and that's representative of an infinitely flat surface. So I don't have to worry about the points being non-coplanar. So the big thing is non-collinear. Yeah, we can't draw a single line through those 3 points. So A, C, and D, an example of that. Some people kind of mess this one up here. We got X's here, so find yourself. Who are we picking on here? 405. 405 is still in row 14. Remember, your number is going to be in the same row each time, so you can find this really quickly. See your feedback really quickly here. Okay, so if you're 507, you didn't get this one right. You said B, G, C. Yeah, those are collinear, right? Collinear. So those line BC would contain both B, G, and C. So one line contains those 3 points. So those 3 points are collinear, not non-collinear. So it's explained to you here. Okie dokie, stuff started to get a little bit harder on number 3 because, yeah, planes have edges, my friends. Planes have edges. Sorry, planes do not have edges. Hopefully I haven't saying planes have edges too much. Please stop me, right? Stop me when I make mistakes like that, or let me know. Okay, so planes do not have edges. The diagrams imply that they have edges, but they don't, right? They go forever. So if we have 2 planes, this one here is name the intersection of plane R and plane S. Sure, say this is R. This is a demonstration of what R is. This is a demonstration of what S is. They crash into one another. Sure, it looks like kind of the intersection here of the 2 planes would be a line segment. Right? Looks like it would be a line segment. But remember, it's hard to show a plane because planes go forever. Right? Planes go forever. They go forever. They go forever. They go forever. So I drew these lines in here to imply, to show that, like, the idea is this plane goes forever that way, goes forever that way, goes forever that way, goes forever that way. Right? Diagrams are messy if they always put these arrows in here and these lines out here. That's why they save arrows for rays and for lines, right? Because there are enough arrows already. So you just got to know this. You got to know here that these things that are supposed to identify a plane, a flat surface, what they're talking about is the flat surface that would continue onward forever throughout the universe, right? Throughout the universe. Remember, the world is not flat, so it's not going to intersect the Earth at all. It's going to go away, right? It's going to go away. Anyways, so that means our line AB is the intersection. Have the whole explanation down here. So really look at that. You can check out your explanations, and you can email me if you have any questions here, okay? Half credit answer. Somebody said line AB or point C. Well, AB is right. Why are you putting 2 answers down, right? Why are you putting point C? Point C is on line AB. So 2 planes intersect at a line, right? That is a postulate from section 1-9. So this one was a little bit more rough here. Let's go to number 4. This guy, let's maybe do the other block here, number 4. So I think the diagram's a little more pretty. We got ray CA. Yeah, ray CA is obviously the one that's opposite ray CB. So remember, they have to have the same endpoint. So ray CB's opposite ray is ray CA, right? You say the endpoint first, and then it goes that way. It goes the direction of the other point mentioned, CA. So it's ray CA, not ray AC. So that's the one on that. Number 5, a lot of these ones were just kind of like similar to, honestly, the chapter test ones that you did for a homework problem set that Mr. Nee filmed an explanatory video for, right? These are pretty similar in terms of difficulty, and some of the problems are exactly kind of like that. So make sure you're doing those chapter review stuff before we go into a quiz. Should go without saying, but I will still say it out loud here. Okie dokie, this was a little bit tricky in wording here. Of course, I arranged this here. This one was looking for you to create 2 expressions, an expression that would be equal to AC, and another expression that would be equal to AC, but would be half of something else. Half of something else equals AC, and the whole thing of something else equals AC, okay? AC is this one here, and if ray CD is a bisector, that means point C has got to be a midpoint because a bisector intersects a segment at its midpoint. So C is a midpoint, so that means that AC equals CB. That was the easy answer. The harder thing was, well, if this is AC right here, what does AC equal half of? Well, AC is a part of the whole segment. In fact, it's half of the whole segment, right? The whole segment is twice as large as AC because C is a midpoint. So the part is half as large as the whole, as long as we have a midpoint. We know that's a midpoint right there. So AC is half AB. Okay, half AB. We see the answers down there. Oop, and I wrote in the answers as well to both and try to demonstrate to you. Part is circled small here, whole twice as large. Okay, half of AB equals AC. Number 6 here, we got 90 degrees here, 90 degrees here. What do we got here? So these angles. Oh yeah, this is a tricky one here. So, oh yeah, if CD is perpendicular to AB, it's oh wait, no, never mind. If if our angles here are 90-degree angles, what does that say about the segments? Well, it says it means the segments are perpendicular to one another, right? So here you need to make a conclusion about the segments, or segment and ray, right? So you couldn't have said, well, then they're right angles. No, that's angles. They're not talking about angles. They're talking about the segments, talking about the rays. So if they're 90-degree angles here, that means the segment and ray are perpendicular to one another. That's a relationship between lines. They're asking you to talk about a relationship between lines because they're talking about segments and rays. Okie dokie. Number 7. Let's see here. Yeah, check out this diagram. This was pretty sweet. A lot of people. Ooh, man, this is sort of a lot of bloodshed on this one here. A lot of red I'm seeing there. So again, quizzes don't matter, guys. They don't matter too much, right? Just do the best you can do. Right, if you get up that 80%, you're gonna be fine. Grades won't matter whatsoever. But if not, right, you get to a 70, you get a B in the class, it's fine, right? I got a B in geometry, it's all good. Anywho, what must be true of segment AB and ray CD? We did that one. How many planes contain the points A, B, and C? Well, A, B, and C are all collinear points, right? All collinear points. So a line, right? A line is contained in infinitely many planes. So if you have collinear points, they're going to be in infinitely many planes because you have a plane like this that would go through all 3 points, a plane like this that will go through all 3 points, a plane like this. And as long as I rotate this plane a little bit and a little bit each time, right, I'm going to find a new infinite surface that contains those 3 points, right? Contains those 3 points. So I want a lot of people, almost everybody said 2 on this one. 2 planes contain ray AB. They don't say how many planes in the diagram. They should just say how many planes. What do we know about the existence of the amount of planes that would contain 3 points? And that is, we'll jump to the conclusion that it's infinitely many. And I have showed you here plane R, plane S contain line AB, and then I tried to draw plane G, right, which is kind of like coming in diagonal to it, diagonal like this, containing those 3 points. And then another one a little more steeper, right, but also going through those 3 points here, okay? And so those are 4 planes, for instance. And you could just, as long as you rotated plane G just a little bit, you'd find another plane. So infinitely many is the answer to that one. A, what are 3? Oh, sorry. Get back. Oh, dog. What a dog. Anyways, dog barking, craziness. All right, everybody almost got this one right. The undefined terms. Yeah, this is just section 1.1. We had to start geometry somewhere. We didn't define what lines, planes, and points are, right? Those are the 3 undefined terms because we had nothing to define them through. Remember, the first thing to do when you write a definition is to classify something. So a ray would classify as a part of a line, right? So as long as we have an undefined term called a line, then we use that to define other things, right? So space is not an undefined term because space is the set of all points, right? All points all over the place. So we use points to define space, right? Anything else in this textbook is defined, and we can trace back its definition to the undefined terms, points, lines, and planes. Okay, nice job on that one, though, for remembering that here. Okay, this was another thing for the first couple weeks of school. This was deductive reasoning relies on which three things to make arguments and prove new facts. We did this quite a bit, just rattle them off, right? I say this, deductive reasoning. Okay, what are we going to do? What are we going to do to prove a new fact? Okay, we're going to rely on facts, rules, and definitions. Okay, we've now started calling those in geometry have been theorems, postulates, and definitions. But facts, rules, and definitions is sort of more broadly beyond geometry. What you got there? All right, next one here. Do planes have edges? No, they do not. So actually, most people got this one right. So you got this one right, but you got how many planes contain the 3 collinear points? Anyway, yeah, do planes have edges? They do not. They go forever. They're infinite surfaces. Nice job there. Number 11. Let's see what we got for number 11. Okay, so we got here, name the sides of KPL. Yeah, a lot of people got this one wrong, man. I was disappointed about this because you got asked this exact same question in 2 of the late problem sets. The chapter test, it was on there, and it was on another one too, where I'm just like, man, a lot of people don't know how to name the sides of angles, even though it's in the definition. I go over it in a lecture, and we're going to go over it on a Jamboard. So I'm definitely putting this on a quiz because it's not super complicated, right? Not super complicated. So the sides of angle KPL, you got to remember an angle is made up of 2 rays that share a common endpoint, right? A ray is defined as that actually. It's 2 rays sharing a common endpoint. So you have a common endpoint, and that has a special name. It's called the vertex. And then, so remember again, an angle are 2 rays that share a common endpoint. The endpoint is the vertex. And then we haven't talked about the rays yet. The rays are the sides, right? The rays are the sides here. So it should be pretty easy. I'm surprised so many people struggled with this one. Should be pretty easy to read this here. Angle KPL, its sides have got to be ray PK and ray PL, right? Ray PK and ray PL, because P is the vertex, right? We see it here. P is the vertex. And then visually we see PK and PL are the sides, right? We name the 2 rays. That's going to form part of the angle. The other thing is the endpoint, and that's the vertex P. Okay, so try to get that, right? The sides of an angle are rays, right? It's as simple as that. And the common endpoint is the vertex of an angle. Name 2 acute angles. Yeah, almost everybody did get this one right, so let's keep going. You guys know acute from the past and stuff like that, so that one wasn't that tricky. Name an obtuse angle, acute to angle MPN. So more people struggled with this one than I was expecting. So this one here is kind of like multiple things you need to think about. So we have here MPN, and that's a 10-degree angle. So adjacent would be sharing a side, right? Right next to is kind of the way that you think of the word adjacent. Oh, what's the building adjacent to that one? Well, that's the building right next to it, and ideally it also shares a side of the building. Think of that. Anyways, NPM is a 10-degree angle. So the adjacent angle would share a side, wouldn't share any interior points. Remember, the definition of an adjacent angle says that you can't share any interior points. You can share a side, and the other 2 sides are away from one another, right? They share a common endpoint too. That's another thing too. So luckily we don't have any angles here that are shown that don't have P as the vertex. So that's nice. We just need to create an angle, find an angle that had PM as one of its sides. You couldn't have done this one here because this one is acute here, so we couldn't have done something adjacent on the PN side because that's only 50 degrees right here. So here, the only option of this was to go all the way out like this. MPJ is adjacent to NPM, right? They share a side, and they don't share any common interior points. They're all here for the green one. Interior points here are all here for the purple one. And this is 120 degrees because we're going from 0 to 120. So the protractor postulate, 120 minus 0 is 120. And we're good to go, right? There's your answer right here. Number 14, you got this action here. Find the measure of the supplement of angle LPN. Again, more people, I think, struggle with this one than I was expecting. Maybe you're just, because of the 35-minute quiz, you're just maybe going too fast and missed the word supplement, maybe. I think that's maybe what happened with people who said 30 degrees. Although nobody said 30 degrees. One person said 30 degrees. 2 people said 30 degrees. Anyway, this is a 30-degree angle. Remember, the measure of the supplement is 180 minus that, right? So if an angle measures x degrees, its supplement is 180 minus x. So 180 minus 30 is 150. That's how you get that answer. So if we have a 150-degree angle, yep, that looks like it's about 150 degrees, right? And then we'd have the whole 180 degrees accounted for. Number 15, we got this action here. So now this becomes the number gets kind of screwed up here. So you have, it says 15, 18, but it's just 15, 16, 17. Reflexive property, yep, that's the thing. You reflect back onto yourself, right? AX equals AX. Any distance is equal to any itself, right? So the distance is a number, so this actually would be the reflexive property of equality, right? AX equals AX. So distance AX equals distance AX, or the length of segment AX is also a number, equals the length of segment AX. So reflexive property of equality. If you said congruence there, I did give you half credit. Nobody said congruence there because you're saying here distances equal each other. You're not saying that segments are congruent to one another, right? It's something different. Okay, dokie, let's see here. We got 16. We got attitude of both sides. Yeah, this one was a little bit tricky for this one. I think a lot of people saw subtractions here, but you're not justifying that x equals y through subtraction. When the properties of equality are things you're doing to change an equation, right? We start with this. This is our given premise here, our hypothesis of this if-then statement. If x minus 2 equals y minus 2, how are we going to change that equation to justify that x equals y? A property of equality is something that you do to change an equation. How does an equation change? Well, that equation changed because we added 2 to both sides. So here, this is the addition property of equality is the best answer you can say. So that was the full credit answer. I still did give half credit for the subtraction property of equality because you can make the argument that that equation is changing because you're subtracting -2 from both sides, which is fine. Like, sure, you could use the subtraction property to get there, but there's a better answer. And any math teacher, any geometry teacher will say, use the simple one, right? Obviously, get out of here, right? This is the addition property of equality. Next one up here, we have this one. Some people got confused by the parentheses there. They said distributive, but nothing's distributing here, right? We didn't distribute the -2 to the a, -2 to the -1 to make that, what, -2a plus 2. No, we haven't done that here. So this here, when you see parentheses, it's likely something got substituted in for another thing. So here we have 2 equations. This one we started with 2 equations and we combined kind of into one to a certain extent. We basically took part of the left side here. We noticed that that part of the left side here equaled something else, and we replaced part of that left side. We substituted in something that part of that left side equal to. We substituted in there. So this is not transitive. A few people said transitive. Not too many people said transitive. Transitive is when you have 3 expressions, 2 of which equal the same thing. This isn't that. This is an expression equal to a different thing, and then another thing we haven't talked about yet equal to yet another thing. But we kind of have talked about this one because it's part of that first expression. So here we have 1, 2, 3, 4 total expressions that we have to talk about there. Okie dokie, number 19, baby, let's do this. Number 19, we got any 3 points, blank, lie in exactly one plane. Any 3 points, sometimes, yeah, sometimes. So we have an example and a counterexample here. So point, right? Say this is the plane here. The computer screen would be representative of a surface, right? So it's part of a plane. So any 3 points you're putting on a computer screen, right, going to be in that one plane at least. And these are non-collinear points. So any 3 non-collinear points lie in exactly one plane, but any 3 collinear points lie in at least one plane, or in reality, infinitely many planes. So this is my example of 3 collinear points, A, B, and C. And sure, they'd be on the plane that is the computer screen, but they would also be on like another plane that's like slicing up, going through those 3 points of the computer screen, or this way, right? Any rotation of the computer screen, we rotate it a little bit, and we're good to go, okay? So that's that one. We thought of an example where any 3 points could lie in exactly one plane. That's good. But we also thought of a counterexample where we have 3 points and they did not lie in exactly one plane. Remember, exactly one means one and only one. It lies in more than one, right? It lies in more than one plane. So this one is technically a false statement, but we'll say it's sometimes true. Sometimes true. Okie dokie, number 20. What do we got here? Yeah, this one's just kind of, this is easier than I probably wanted these problems to be, although we kind of struggled a little bit here. So this one here, if you're complements, that means you add to 90 degrees. So pretty simple. 3x plus 2. I don't know, show the workout here. I think I should put the answers. But anyways, 3x plus 2 plus 5x minus 8 equal to 90. And then solve it algebraically, right? Solve for algebraically. This is, and then some people solved it algebraically, got x. Like this person got x equals 12. But the question was, find the numerical measures. So you got tricked there. I always got to be like, am I solving what I'm going to be asked to solve for? You need to find the measure in the angle. So 3x plus 2 plus 5x minus 8 equals 90. Solve for x, you get 12. You got to pop back in here. So 3 times 12 is 36, plus 2 is 38, and the other one would be complementary, so it'd be 52. Okay, so if it's vertical angles, they equal each other. I might put a little explanation down here too. I don't like that I didn't actually show the algebra, but this you would just set the equations equal to each other. 3x plus 2 equals 5x minus 8. Solve for x, boom, but don't just stop after you've solved for x. You guys solved for x, and you got 5. So x is 5 here, so that means our answer is 17 and 17. 3 times 5 is 15, plus 2 is 17. All right, man. Oh, proof. Do I have time to go over this one? Man, this video has been long enough, I think. I think I need to wrap it up, guys. 20 minutes, and you're not going to watch this video anyways. Just watch the whole thing of this. I guess you watch some problems you didn't get right. Okie dokie, this problem here, there were only like, I think 5 or 6 people who got full credit on this. That's okay. It was only worth 4 points, and I gave you partial credit. Okay, so remember the 4 required parts of the proof. Diagram, given, proof statements, boom, that got you a couple points if you just did that. Then you got your statements and reasons. This here is what the book had kind of intended. Chapter 1 isn't a great chapter for writing proofs because you're learning all these kind of different things that don't really connect that well together. So I wasn't expecting that many people to get this one right, but again, it was only 4 points. So I wanted to see how close you could get. So this person did get full credit, 4 points here. So they use their givens as the first step. I agree with that. That's 90% of the time. That's what you're going to do. If ray AB is perpendicular to ray BC, and angle 1 and angle 2 are complementary angles, and the reason I know that is because that's a given premise to me, then I can say angle 2 is complementary to angle 3. The reason why I can make this conclusion is because if 2 exterior sides, this is what we're talking about here, 2 exterior sides of 2 adjacent acute angles, so AB and BC, are perpendicular to one another. So because we said this in step 1, we can conclude that 2 and 3 are complementary angles here. So if 2 exterior sides of 2 adjacent acute angles are perpendicular, then the angles are complementary. So you had to maybe have that Jamboard open that had all the reasons down. So maybe like find that one, be like, oh, I did learn that one. We did use that a couple times. So this is the way to get it done in 3 steps. It's still possible to do this in more than 3 steps. Some people did. You would just have to go about showing that these 2 angles added to 90, and then these 2 angles added to 90, and they equal each other, and then subtracted things, and all that good stuff. So kind of messy to get it inside this here. All right, anyways, so angle 1 and angle 2 are complementary angles. Angle 2 and angle 3 are complementary angles. Whoa, what do we know about angle 1 and angle 3? Well, they got to be congruent to one another, because if 2 angles are complementary to the same angle, then the 2 angles are congruent. I'm willing to go over this one a little bit more slowly with you guys later if you want. I just want this video to be a little bit shorter here, okay? So definitely read my feedback, though. I pointed out some things. Another common thing that I see at the beginning of the year that I just drives geometry teachers nuts, but like is an important thing for you to notice here. A lot of people weren't putting the m's down to say they're talking about angle measurements. Remember, if you're setting up an equation, you need to be talking about numbers, and measurements of angles are numbers. So don't just draw the angle symbol and say angle 1 plus angle 2 equals 90, right? You have to say m. That means measure of angle 1 plus measure of angle 2 equals 90 degrees. Okie dokie, bonus here. Yeah, this little algebra problem. This, again, was a little easier than I wanted it to be. I think people just ran out of time, didn't have time to do this one here. But anyways, answers up here if you want to check it out, and I'm willing to go over it if you guys want to. And finally, other bonus here, which was the Lincoln on Euclid. 2 things that are each equal to the same thing are equal to each other, using that to argue that all people were created equally. Therefore, 2 things, enslaved people, enslavers, non-enslaved people, abolitionists, right? We're all the same, right? We're all equal to each other because we're all people, right? If all people are created equal, then we're all people. We should treat people equally, right? Which is kind of cool about that. That got served into so much of Lincoln's writing over a couple decade period. Okie dokie, that's it. That's me going through the quiz. I would never do this entirely, go over the whole thing in class. I probably have you look at it with your groups. But let me know if you have any questions, and I will see you guys tomorrow. Take care. Bye.